G'day everyone and welcome to Step Forward Prosthetics. Today I'm going to be showing you a guide to create your own 3D printed prosthetic sockets for a fairly cheap price. So what are you going to need? You are going to need a computer with a 64-bit processor, 3 gigabytes of RAM and 2 gigabytes of spare disk space. This is a fairly low system requirement, so you do not need a crazy PC or laptop to complete this task. You are also going to need an iPhone X or newer. Unfortunately, this cannot be completed with an Android phone as you need the iPhone's face scanner. You're also going to need a 3D printer, and this is the most expensive aspect of the entire prosthetic socket. So due to the size of most residual limbs, you're probably going to need a printer with a 300 by 300 by 300 millimeter print space, which is fairly large in comparison to more hobby 3D printers, which are around that 250 millimeter print space mark. So you can also reach out to places that will print 3D printed models for you if you send them the design. So that could also be an option. Or if you are in university, most universities have access to 3D printers, so you could talk to them as well. You also need a small selection of hardware. You need a soldering iron and heatset inserts, which can be found online for fairly cheap. So what software are you going to need? You're going to need Autodesk Mesh Mixer, which is a free downloadable uh, mesh software. So it's designed mainly to just edit and sculpt meshes. It's fairly simple. It's not too large of a learning curve to sort of understand this software. You can get that from Autodesk or from Softonic as well. You also need Autodesk Tinkercad, which is a free online CAD software. You need to create an account with Autodesk to access this. However, the accounts are free, and if you are with a university, you can create a student account as well. But there's no difference between the free online account and the student account, so you're good to go. The app that we used was EM3D from the App Store. You could purchase two different versions of the app. You could purchase the $9.99 price, which would just allow you to export the STLs, or you could purchase the full version, which was around $30, $29.99. You do not need the full version for this. You only need the light version. However, the transfer of STLs using the light version can be a bit difficult because the STLs can get quite large. So that's something to think about as well when you're doing this. And 3D printer slicer. So depending on what 3D printer you're using, you'll have to download the slicer for that specific printer. All of them are free, so it's not too much of a hurdle. As well as if you've got a place on university to print them, they'll have their own slicers that you can go in and play around with. So the first step is scanning the patient's residual limb. You have to ensure that the patient's residual limb is clean, no debris, no dirt on it. Also, you'll have the patient laying flat on the floor with their residual limb vertically upwards. It's best to place the limb against a table or a solid object so that the patient can't move their limb. So you also need some lights around to scan it. Good idea is to do this outside during the day, cloudy day, not direct sunlight. That provides more than enough light. And you have to make sure that you can easily walk around the residual limb. You'll probably have to walk around 30 centimeters, the phone from the residual limb. So just do a quick run around before you do it to make sure that you've got enough space. And then scanning. So on EM3D, you'll start up the app and it'll tell you how far you'll need to go away from the residual limb to scan it. And the app will show you all this. So just follow that through. And what we did was we did at least 3 full rotations around the residual limb at variable heights. I'll show you that next, what I mean by that. So the first rotation we've got here on the left, I've done it pretty much perpendicular to the limb and just slowly and steadily going around this limb. I've printed out a 3D printed replica of a clinically scanned limb to complete this task. And then when we move on to the second rotation, I've moved the phone up slightly higher, getting a bit more of an angle down on the limb to just grab more of the mesh areas on there. And then once we move over to the third rotation on the right here, I've gone all the way to the top to get the bottom of that residual limb around where the femur would sit, just to make sure that that bottom part of the residual limbs mesh is fully defined. And then once you are finished scanning the residual limb, click the red button to stop scanning in EM3D, and then have a look at the mesh after you've done, and ensure that it's fully complete. There's no holes in the mesh. It doesn't look funny. It doesn't have, certain parts sticking out where they shouldn't. The app will show you the mesh in color, so it makes it a lot easier to actually see if anything's gone wrong. It may take you a couple times to get this correct. I found that placing a square object close to the limb that you're scanning that's visible from all angles will allow the app to continuously track that object and then fill in the rest of the residual limb. So it makes it a lot easier and less trial and error. And then if you've got the light version, you'll save that to an STL and export that onto your computer. You may have to use something like Google Drive to move it over, as on the light version the STL files can be fairly large. However, if you've gone for the full version, you can open the slice mesh option in EM3D and delete everything except for the residual limb, and then export just that residual limb STL, and you can send that over pretty much anything: Discord, Gmail, Google Drive as well. Just a lot smaller STL, which makes it quite easier. Alright, now that we are finished with scanning the residual limb, we're going to head over to Tinkercad on our computer, tinkercad.com. You might have to set up an account if you do not already have one. And we're just going to start a new 3D design. And in this 3D design, we've got our workplace here, and we're going to put a cylinder anywhere on the workplace, doesn't matter. We're going to want this cylinder to be 70 millimeters in diameter, so we'll change both of these values to 70, and then we want it to be 30 millimeters tall. So that is that there, and we will click export and export that as an STL. Alright, now that we have the base plate and we have the STL files of the residual limb, we're going to go ahead and import those STL files into Autodesk Mesh Mixer. So we'll grab a file, open that, and now you should have your STL file in Mesh Mixer. Now the first thing that I like to do is I go to align the base point to the ground plane and translate only. Click accept on that, and then I'm going to go to transform, and I'm going to look at the front of it here, and I'm just going to try and align the scan pretty much vertical. Every time you make a movement, it's going to change this XY transform movement. So to accept it, then click align again. Make sure that's on translate only. That's going to reset the whole socket. So then when you go back to transform, it has the XY vertical into the side. Makes it a bit easier when you're making sort of finer adjustments. Another good thing to do is make sure that it's straight. Should be fairly straight. Doesn't overly matter, but it can make a bit of a difference. But yeah, that looks pretty upright to me. Just looking at sort of straight lines on each angle. Looking at the back there, might just move that. Nah, keep it straight. Alright, now if you have imported the STL straight from EM3D and didn't refine any of the mesh within the app, or if you just couldn't quite get everything in the app, a good thing to do is to go to select, and you can paint select any of the mesh faces that you don't want. You all of that, and then click delete on your keyboard, and that will get rid of everything that you've selected. Another way to do this is to go to edit and plane cut, and sort of just take that up to above the side of the knee, nowhere that you're going to need to make the socket. And we'll change that to keep both and no fill. Click accept, we'll go back to select, put this down, and double click on this top part here because we want to delete it, and we'll go to delete. We'll get rid of that. So that's just to refine sort of the mesh a bit more to make it a bit easier to design the rest of the socket. Okay, now that we have our residual limb mesh all lined up and reduced, we are going to go ahead and make this a solid. Might take a second, shouldn't take too long, but this will just allow us to easily select all of the other faces. When you do it as just as the mesh it is itself, can sometimes do some funky things which mess everything else up. So it's easier to change it to a solid to begin with. We're going to bump this solid accuracy all the way up and click accept. It will open the object browser. This is quite handy to have. You can close it and open it again, but it is nice to keep open. So now that we have that a solid, we're going to go to select and begin to select our socket area. I'm going to bump this all the way up to 80 just to get this bottom area first. Make it nice and quick. Make sure you get the bottom as well. And there we are. I'm going to push that down a bit small to around 50. And we're going to start with the back here. So we want the socket to come up to below the knee on the back. Don't want it to go too high because the leg will bend, and if it's too high it'll come in contact with that. And then on the side of the knee, we want that to come pretty much all the way up to the top of the kneecap to give some support to the patient. Pretty happy with that. If you make a mistake, you can click Control to delete the selected areas, but that looks good. We're going to go to the front, and we want to come below the top of the bottom of the kneecap there, and then the same thing on the other side. We want to come up to the top of the kneecap on the side of the knee. Now that looks pretty good. Let's have a quick look around, make sure they're pretty much the same height on each side. That looks good. It's not too high here, and it's not too high on the back there either. So that's perfect. We're going to go and click B on our keyboard. It's going to make a smooth boundary on the top of that selected area. I like to bump the smoothness all the way up and the preserve shape all the way up. Makes the lines flow a bit better. Well, we do not want anything selected down the bottom here, and we're going to go ahead and click accept. Now we've got nice smooth lines everywhere, and from there we're going to go ahead and click on Control G. It's going to separate that selected area. We'll go back to select, pick that back up again, and we're going to create an offset now. So Control D. May take a second again. And here we go. I'm going to click off connected to begin with. And we want the distance to be 5 millimeters. There we go. And you can see that it's separated from the residual limb there. So this will account for volume expansion of the limb when it's in the socket, as well as a sleeve that will go over the socket, over the patient's residual limb when they wear the socket. So that's good. Doesn't matter if there's a few sort of rough bits there, we'll fix that up later. So we'll click accept. We will then click escape, and we'll select that outside bit by double clicking. Perfect. And we'll make another offset here. We'll go Control D again. And this one we will make 10 millimeters thick, because we want the socket to be 10 millimeters thick. And once that has loaded, we're going to click on connected. And that will connect the two layers together. Perfect. All right, have a look through, make sure everything is fairly all right. We've got a bit of a situation going on here, but we'll fix that up. So we'll go accept. And now any areas that are connecting from the socket to the limb, we want to clean that up. So we're going to focus in on this one here. We'll smack down this size, about 9, and we're going to select these areas. We'll click escape first to deselect everything. And now we just want to select the areas that are not in the general sort of line that we've got going on here. Can do some funky stuff sometimes, so it's best to really sort of focus on what you're selecting. Can be quite hard to pick up some of these areas sometimes. And you might have to move this around a bit to sort of find them. So yeah, and click delete there. And we'll see there's still some more that we've got to get rid of. Trying to find the actual outside surface sometimes is hard, but just give it a good old crack and it should work out in the end. There we go. As soon as you start deleting some, they will become more sort of available to see. If you select some of the back area, just control that out. That should be good. Now we'll click I on our keyboard. Oh, click escape first, sorry, and then we'll click I. It'll pick up this area here, and we're going to click auto repair all. And that has fixed that up. It's not perfect, but we're going to smooth out that area in a second. Just ensuring that nothing goes from the socket to the limb, and then everything will be fine. Okay, perfect. So now we're going to click done on that. And we're going to go back to select, change the expand mode to crease angle, and we're going to double click on the top surface here. Now we want all of this top surface to be selected. So we're also going to select this area that we fixed up. Just like that. And have a little look around, make sure everything else is selected. That all looks pretty good. Now we're going to change this expand mode back to geodesic distance. Click Control, right mouse button, click on here, and then we're going to go upwards and to the right, and that's going to expand our selection out. This part's going to be curved and smoothened out, so we don't want to go too far. Just want to go a little bit. We can have a look around and see that that looks all good. And that is quite alright there. So now we're going to go Control F on the keyboard to open the smoothing tool. And you'll see that that's started to smooth out that top surface there. Now we want to move this smoothing scale all the way to 100. Now that's super smooth. That looks very nice. Perfect. And we're going to click accept on that. And there we have it. That is most of the socket done. So just having a look around, making sure everything is all right. Still nothing connecting between the two. That looks good. All right, now we'll move on to separating the socket from the limb. So we're going to click escape. We're going to click select, and we're going to double click on the limb and also double click on the shadow here of the socket. There we go. That's got that all selected. Click Y on your keyboard, and now we have selected the socket from the limb. You can see in the object browser, we've got the socket and we've got the limb. So we want to hide the limb for now because we don't need that. And we'll click on the socket. And there you have it. You can inspect the inside now, make sure everything looks all right, which it looks pretty good. Okay, so now that we have the general shape of the socket designed, we're going to go ahead and move this socket upwards. Move it up about 25 mil here. Accept that. And we're going to bring down this inside part to move it further away from the femur, as there isn't a lot of tissue around the bottom of the residual limb near the femur. And if that comes in contact with this socket, it can be quite painful. So if we go to plane a cut, and we'll line that up here, go to the bottom, the very bottom of that socket is about 25 mil. So we'll move this up to around 50. This can be patient specific, as if the patient has a large area of exposed femur, you might want to move that up a bit higher to accommodate for that, or you can move it lower. It all depends on patient preference. So we're going to go to cut type and change that to keep both and no fill. We'll click accept on that. Now we'll navigate down to the bottom here, go and select and double click this bottom part. We want to get rid of that. So click delete. You can see that there's also a cut on the inside here. So if we move back up and we double click that area there and go and press Y on your keyboard, that's going to separate that from the rest of the socket. So now that we have those parts separated, we can go ahead and click edit and transform and actually bring this down lower. So depending on how much the femur is sticking out, depends how much you can move it down. We're at 43.75 here. So if we go down to around 25 mil, that gives us a good clearance without making it too far of a distance. So we'll place that there, click accept. Now using the object browser here, we're going to select on the socket and select on the bottom of the socket. We're going to combine these two together, and now they're back together and they're both under the same object. From here, if we zoom in, go back to select, and we want to select just on the very bottom outside here, double click, get that thin line across there, and we're going to do the same for the bottom here. Double click. Now both of them are selected. Press J on our keyboard, and there we are. That's connected both of them. You can see on the inside too, that's connected there. Click accept and escape, and now that is all good and done. I'm gonna go edit, align, change that to translate only, and accept. And there we go. Now we're back at the bottom there, and we've got that extended part. Okay, so now that we have that part of the socket design, we're going to go ahead and import the base plate that we made in Tinkercad. So click append, and we're going to import that there. Go to edit and make solid, and let's bump up that solid accuracy. Perfect. So let's navigate back to the socket, and we're going to make some room and move this up. So 150 now. Go up 50 mil to leave that there. Click accept, and perfect. All right, so we'll click back on the base plate, go edit and align to translate, and base point. There we are. Click accept, that's there. Go to select, make sure that's on crease angle. Do a small circle here with control and right mouse button, move up to the left, and delete the top of that cylinder there. Perfect. Now we want to align the bottom of the base plate and the socket so that they're fairly in line with each other. We can do this by going to transform, making sure this is straight here, and just lining these two up so that they're fairly straight. That normally doesn't need too much of a change. Click accept on that. If we move around to this side here, we can look at that, and that looks pretty good. If we move that around, it's good where it's at there. Perfect. Now, if we have our solid base plate selected, and we control, and we click our socket, we're going to combine those two together. Combine. Perfect. Now those are one part. And we're going to do the same that we did with the bottom part here to join both of these sections together. So first things first, we'll go to select, crease angle, and we'll select the outside there. Then we're going to come down here, and I'm going to select the top there. That wasn't really good. We're going to select the whole section there. It's only going to connect to the top, so that will be good, and it's a bit of an easier way to do it. Go to J on your keyboard, press that down, and give it a second to load. This is normally the most demanding part of the whole process computationally, but it should work after a second. There we go. We can see there that the two parts are connected. Can have a look around, make sure everything looks pretty good. Looks pretty alright to me. We'll go accept, and we can go Control F. See if we can smoothen this area out a bit. Normally whack it straight up to 100, and that looks pretty good there. Click accept. There we are, we're almost at the end now. Now that we've got those two connected, and that's infilled in that middle part there, we can go ahead and go to edit and make solid. So we'll make the entire thing a solid, which has worked pretty well. You can see at the bottom here that doesn't do too well with these harsh edges, but that's okay because we're going to delete that part. So lining up straight with that, I'm going to go to plane cut, and you can see here that all that inside area is filled in. So if we bring that all the way down to 0, we go up, this was 30 millimeters high, so we go to 25 to give it just a bit of flat space at that bottom pit there. We'll go with cut, discard half, and remeshed fill. Click accept there, and there we have a nice flat surface at the bottom there that we can use to connect with the rest of the prosthetic system, and the rest of it. The mesh looks pretty good. Another thing you can do, if you see here, there's a bit of a sharp turn. It's not too bad. You can go to sculpt, change that to surface, just on the low setting there, 20 strength. Maybe increase the size slightly. You can run around the outside here just to sort of flatten out those areas. Doesn't make any difference to patient comfort, but depending on patient preference, how they like the look of their sockets, you can do this. It does add just a bit extra to it, but again, not a vital step in the process. So yeah. Perfect. Now that that's done, we're going to go and click export, and we're going to save this as an STL file. And move on back to Tinkercad with this file. Alright, so now that we have the prosthetic socket in Tinkercad, we're going to go ahead and flick the socket 180 degrees around. So there we go. Click away to accept that. Now we can easily work on this baseplate connection here. So we're going to go to the work plane tool and put a work plane on the flat area there. I'm going to go ahead and grab a cylinder and place that on the top there. And now we know the base plate there is 70 millimeters in diameter. So we'll put 70 on both of those there, and then line this up like so. There we go. We can see that that's aligned. Now we'll change the height here to 5 and click away. This is just so that we can get the center of this base plate. So importing a ruler in the middle there, and then changing that to use the edges, we can position this ruler so that both values here are 35. Might take a bit of playing around to do, because Tinkercad is not a very advanced piece of software, so you might have to just play around a bit, write in some values, and then move things back. But there we go, we've got 35 and 35. So we know that this spot here is the center of this cylinder, which is the center of the connection port down the bottom there. So we're going to click away from everything there, go to these hollow cylinders on the right here, and transport one in. That's going to move the ruler to a different spot. So what we're going to do is click escape, and the spot will go back to the center there. If you don't click on it, which I just did, that's okay. If we click on that and that, we can move that back into the center there. Perfect. So ensuring that you have clicked these 3 lines here so that you can see these green lines go to the middle of the cylinders, we can change this cylinder's diameter to 7.5, which is the diameter we want for the heat set inserts. And now we want these hollow cylinders to be 15 millimeters away from the center in both directions. So now that that one's set there, I'm going to click off it, copy this, click off, and paste it. Now we can move this one to the right here. We also want that one to be 15 millimeters away from the center. So we're going to click off again, click this one, copy, paste, and then drag this one over here. We also want this one to be 15 away. Some of them you'll have to make negatives just due to the orientation. That's done there. Click away, click back on, copy and paste, and move this one over to this side. So negative 15 and negative 15 again. That is good. We're going to click off again now. Have a look at everything. We can see some of them are different sizes. That's just because this is not flush with the surface there. So we can drag that up. Now, we want the heat set inserts to be 6 millimeters into the rest of the socket. So we're going to change the height of these cylinders here to 6 mil. So we can drag that down all the way to to 6mm. Which seems a bit wrong. Oh, I was looking at the wrong one. There we go, 6mm there. We can drag this down to 6mm. Some of the views in Tinkercad are quite hard to sort of move around and see, but as soon as you move everything around to different sort of views, you can tend to get a better view of everything going on. So there we go. We've got all of the heatset insert holes prepared there. Now we know that this is 5mm tall. So we're going to have to move these down an additional 5mm. So if you look on the right there, we've got 8mm to be flush with the top of the prosthetic socket there. So we change this to 0. They should go all the way down to be flush and flat. We'll also double check this at the end, so if it hasn't worked out, we can always change them at the end after we know that they're in the correct position. So all of the heatset insert holes are now set in there. We also need to include a hole for the remainder of the bolt. So we've got M6 bolts, and they're going to be 30mm long. But there's going to be a 5mm base plate on top of the bottom here. So we can make the height of these 25mm, and then we need a 6mm diameter because there'll be M6 holes. So we're going to click off that to return this ruler to the center there. Click back on it again. And we also want these to be 15mm away from the center so that they align with the heatset insert holes. So we're going to click off, click on that, copy and paste, move that one over to the other side, and change the values to all 15. Click off, click on, copy paste, move that down here. It is quite the process to do it this way, but it does save a lot of time later on when you realize that it's actually not aligned. So this way we can ensure that everything is straight and aligned. So there we go, we've got everything aligned there. You can see these all sticking up here. If we grab these all, we can check they're all 25. And now we can move them down. If we move them down to where it says 0 there, we know that it's not going to work. So make it flush, -7.5, and then take off another 5. So we've got -12.5. Now we can do the same for all the other ones. And again, sometimes if it doesn't work, that's all right, because we'll double check. So we can change it at the end. -12.5. All right, click off from that. And we're going to click on the cylinder here and go delete. We're going to get rid of that. And we can see here now that just some of them aren't flush yet. So we're going to drag them down. 3mm. There we go. Make sure that everything is nice and flush, and we can check on the top. We can see the clear 2 different circles there. So that is perfect. We can now click off of that, and now we have the holes that we can connect the rest of the prosthetic system to our prosthetic socket. Go ahead and export this as an STL and import it into your 3D printer slicer software. Okay, so now that we are in the 3D printing slicing software, here I've got the Aligu software. I've just selected the Orange Storm Giga printer because it's the largest one that they had there, just to show you how this process will work. So we'll go ahead and we will import our STL file, and it will come in upside down because that's the way we were designing it in Tinkercad. But that's all right because we can check out the bottom here and make sure that these holes are all good. We can see they've got shelves there, which are perfect, and they are all lined up. So then we can go ahead and lay on face or rotate this around 180 degrees, but just click on the bottom there and that will flick that around for us. So there we go, we've got our socket placed in the printer, and then we'll go ahead to the strength section, change the wall loop so that it says 4 and the sparse infill density at 100%. We've got a rectilinear and a monotonic infill here as well. So from there we can go and slice all, which will generate the G code for the prosthetic socket. Now this G code is going to be fairly long because it is a large object, but we can also see here that we've got enough space between the screws and the bottom there to make sure that those screws don't go through. So that is very good. Might take a second to load, but there we go. So this is a very large build. We've got 1 day and 10 hours of print time and 1,300 grams of filament, which is a lot. Most of the filament comes in 1 kilogram rolls, so you may have to pause your build halfway through, change the roll over, and then continue building after that. But from here, you will export the G code to a USB and then plug that USB into the printer and begin printing.
So after the 3D socket has printed, you're going to need to insert the heatset inserts onto the bottom of the prosthetic socket. They'll fit nicely on top of the holes that we designed earlier. I've got these two on the left that I've already put into the socket, and then this one here on the right that's just sitting on top. I've got a little adapter to put the heatset inserts into the socket, but you don't need that. You can put the socket directly, you can put the soldering iron directly on the heatset insert. And I'm just using the weight of the soldering iron in my hand to sort of push this down. As you can see, it takes a little bit of a while. This is at 2 times speed here. So if I skip it ahead, you'll see that it slowly goes into the bottom of the prosthetic socket there. You don't want to do it too fast as it can cause the outsides of the filament to crater around the top there, which doesn't allow for a flat surface on there. But make sure that you get the heatset inserts all the way in so that they're flush with the bottom of the prosthetic socket there. As an extra step at the end as well, we've added some 2-part epoxy to the inside of the prosthetic socket. This can help smooth out the inside area, makes it a bit softer on skin compared to the PLA finish. It also increases the strength of the PLA plastic here, just adds a bit more to it. As well, we've added some sports cushioning tape to the pressure sensitive areas of the residual limb, so anywhere that's pretty bony and doesn't have a lot of protective tissue around it, tibia there, on the sides of the knees, around the bottom and the back. Just added another layer of protection for the patient. If we can go flick around there, yeah, you can see all that on the side. But this is a good extra step to make the prosthetic socket a bit more comfortable.
So here I have some videos of us printing some of these prosthetic sockets at half size. So we've got one here that we printed at a 45-degree angle, which was a bit more difficult because you need supports. It also messes up the bottom of the prosthetic socket. It's not as straight. Then we've also printed other ones that were upright instead of at that 45-degree angle. You just look at about the size concerns printing it upright compared to on that 45-degree angle. as well as the 45-degree angle one and the upright one. We did a compression test on both of them, and the upright one performed a lot better than the 45-degree angle prosthetic sockets. So that's another thing to think about when printing these sockets. I've also going to include a list of written instructions as well as this video. The written instructions go a bit more in depth with why everything's happening, as well as provide all of the shortcuts that you need on Mesh Mixer and Tinkercad. So those will also be available for you to download and read. But other than that, thank you for following along. I hope the guide was useful, and all the best.